In this video, we're going to try to figure out the relationship between voltage and current on a transmission line. We need to think about this because the telegrapher's equation solutions tell us the voltage on the transmission line, but not the current. We'd like to be able to find the current anywhere on the line too. Fortunately, we have an easy tool to do that, because each differential segment of a transmission line has some impedance. If we find this differential impedance, then we can just divide V of xt by it to get I of xt. We give this differential impedance a special name, the characteristic impedance, and we give it the symbol Z0. You might notice that we've opted to use a capital Z, which suggests this has units of impedance, not impedance per unit length, and that suggestion is correct. As a side note, we're assuming constant values of R, L, G, and C across the transmission line in this derivation. That's a safe assumption for most modern transmission lines, but some people violate that assumption on purpose to build microwave devices. It's also a property that sets transmission lines apart from random wires on a breadboard. Okay, to get started, I've included an equation for the impedance seen by V of xt up here. You can see that it's the sum of the impedance of the series elements, this term, plus some complicated shunt element, this term. The shunt element is made of two parts. The first part describes the effect of capacitance and inductance. Conductance. This equation opts to represent the impedances of the inductor and the capacitor as 1 over their admittance. And admittance is 1 over impedance, so it's just like a complex version of conductance, just like impedance is a complex version of resistance. The admittance of a conductor is just G, and the admittance of a capacitor is 1 over the impedance, so it's j omega c. And finally, admittances add for parallel elements just like impedances add for series elements. So we're left with an impedance of 1 over G plus j omega c for the conductor and the capacitor. That impedance is in parallel with Z0, which might seem surprising. This Z0 term comes from the fact that our differential wire model is a two-port model. So we have to hook something up in parallel with the conductor and capacitor to represent what the V of x plus ds port is connected to. The trick here is that the segment we're looking at is differentially small, so removing it won't change the impedance seen looking into the rest of the transmission line. That means we see Z0 looking into the V of x plus ds port too, so over this way we would see another Z0. Alright, with that equation set up, we can do a bunch of tedious algebra. I'm going through some of the details of it because there's one step in the middle that's a good reminder of some common physics approximations. But overall, this is just turning the crank. First, we make an algebraic expression for two things in parallel. Then we multiply both sides by the denominator of the second term on the right. That leaves us with a messy equation, but there are a bunch of ways to simplify it. We can subtract 1 from both sides, and we can also throw away the first term of the second equation in this sum, because it will wind up being multiplied by ds squared, and a squared differential is too small to care about. So we're left with a much more tractable equation. And we can go through and solve it to find the characteristic impedance, which simplifies nicely when we assume it's lossless. So note that the ds variables cancelled, so this differential impedance, so this characteristic impedance isn't multiplied by ds, it's just an impedance. But it happens to be a ratio of two impedance densities, that's how we get to it. Also note that the impedance has two solutions, there's a plus or minus in front of it. That's because one of these solutions corresponds to forward traveling waves and one corresponds to reverse traveling waves. The negative sign just means left traveling waves send current in the minus x direction. It's not that there's like negative resistance generating power or something like that. Before we go any farther, it's important to get some definitions straight. We use the word impedance a lot in this class, but it can refer to several different things. Lumped impedance is normal impedance. It refers to like a discrete capacitor. This is what multimeters measure because they only measure DC things. Characteristic impedance is a property of transmission lines that describes how a differential segment behaves. The only things that interact with our distributed model are waves. So we can only infer the value of Z0 by looking at how waves propagate and interact. We'll talk about some tools to measure waves soon. Also, note that 50 ohms is a common characteristic impedance for rather silly historical reasons. So if someone says a cable is 50 ohms, that's referring to a characteristic impedance and not a lumped impedance. A multimeter won't measure 50 ohms on a 50 ohm cable. Driving point impedance is a fancy version of Thevenin impedance. This is the impedance that a driver perceives when it looks into a length of transmission line. It's important because we're going to see that the driving point impedance can change with time as left traveling waves go back to the driver. Finally, radiation resistance gets an honorable mention here, even though it uses the word resistance and not impedance. Radiation resistance is a property of antennas, and we won't see it for a while, but keep an eye out. So, we're going to start exploring these different kinds of impedance by calculating the driving point impedance of a transmission line. To do that, I've drawn a schematic here that shows a step function being driven into a transmission line. The function generator in this case has a source impedance of Zs. We're calling the node between Zs and the transmission line V of 0t, and the current flowing in the transmission line I of 0t. The driving point impedance is V of 0t over I of 0t by definition. Right? Impedance is just a ratio of voltages and currents. And we can then substitute in for I of 0t because using our characteristic impedance, we know that I of 0t has to be V of 0t over Z0. That means overall the driving point impedance is equal to Z0 in this example. Even though I've promised driving point impedance can vary with time, it isn't doing so here because the transmission line is infinitely long. The value of driving point impedance has a few other effects. First, if we look at the wave propagating down the line, we can see that the height is set by a voltage divider between Zs and Zdp. So this voltage on the line is given by Z0 over Zs plus Z0. Second, we might also notice that Zdp is a real impedance, which suggests that our power supply is dissipating real power in it. That's weird because this is a lossless transmission line made entirely out of lossless inductors and capacitors. However, we can resolve that paradox because, from the perspective of the power supply, it appears to be losing power down the transmission line. It throws power into it and it flies away, propagating down the line forever. So, in summary, we can find the current in a transmission line by taking V of xt divided by the characteristic impedance Z0. Z0 is called the characteristic impedance, and for lossless lines, it's equal to plus or minus square root of L over C. The driving point impedance of an infinite transmission line is Z0, and impedance can mean a lot of different things in this class, so be sure to be specific.